Hi, everyone. Thank you for joining the Macro Energy System Expert Panel. Today, we have a wonderful panelists to discuss data centers. Let me introduce our moderator. So, Jesse Jenkins, who is an associate professor at Princeton University, and it's leading the Zero Lab, um, Zero Carbon Energy System Research and Optimization Laboratory. Over to you, Jesse.
Thanks. Thanks everybody for joining us for this MES Expert Panel. I'm excited to be joined by two of my esteemed colleagues, Michael Weber and Eric Masanet. Michael is a professor in the Department of Mechanical Engineering and the John J. McKetta Centennial Energy Chair at the University of Texas at Austin, where his research focuses, like many of us, on energy systems, electricity grids, water resources, decarbonization, and the intersection of technology, policy, and sustainability. Eric Masanet is a professor in the Department of Mechanical Engineering and the Bren School of Environmental Science and Management at UC Santa Barbara, and where his work focuses on industrial energy systems, energy efficiency, data centers, clean manufacturing, and pathways for industrial decarbonization. So delighted for you to both join us. I should also note that I've been working over the last year as co-founder and CTO of Firma Power, which is a company that works to supply clean energy to data centers. So I've been sort of living and breathing this space for the last while. And excited for the conversation. And I think, Michael, we'll start with you for some introductory remarks on kind of how you see the challenge of AI and data centers and how those are shifting our expectations for energy system planning and maybe the role that the MES community might have in trying to guide that transition.
That's great. Thanks so much. And I'll just make some comments. I don't have any slides or anything, but I'd say it's a pretty exciting time to be in the energy space or energy, water, land, and intelligence space because so much is happening. There's a lot of investment. Investment and the pace of the investment creates a lot of risks of downside impacts. We might invest the money in ways that we really regret and be locked in for many decades and stuck with those decisions, but also might let us invest in ways that unlock the things we really want, which is kind of cool. And I will say that I've got a couple different perspectives. I'm primarily a professor, but I also had worked in Paris for a while at Engie, a big multinational energy company, and I also worked for a while at a venture fund, Energy Impact Partners. So I'm kind of a professor or entrepreneur or venture capitalist or multinational corporate guy. But I think the most important perspective I bring is the view of a Texan. I'll try not to do too much Texas patriotism on this call, but Texas is an interesting place to study energy because we're doing so much of it at such large scale of everything except for hydroelectric, where we don't have much water. But we're building a lot of things, and we're also building a lot of data centers. And the data centers are really robust in Northern Virginia, but the pace of construction in Texas is such that Texas might overtake Virginia for total capacity it relatively quickly. And it's kind of some question like, well, why Texas? Texas isn't necessarily the hotbed of where the telecom companies are, except that AT&T is headquartered in Dallas and used to be Nortel in Dallas. So we're some telecom companies. But Texas has a good combination of fiber optics, transmission lines, natural gas pipelines, railroad, flat land, and maybe water in some cases. But in particular, Texas can connect new loads to the grid quickly. And that speed to power is pretty interesting for Texas. So that's where we are right now, where we're feeling the impacts of all these new data centers getting built, and maybe they're competing for people for the power and for the land and the water. And the benefits of those AI data centers have not been felt, might be felt someday, maybe higher tax revenues, maybe a better grid, maybe a cancer treatment or something. But we're feeling the impacts today, but the benefits come later. And that mismatch is pretty fascinating. And as a consequence of all these ingredients coming together, the load growth in Texas is just off the charts. Like it literally goes off the graph. Our peak demand in Texas is about 85.5 gigawatts. The projected peak demand this summer is probably 92 gigawatts because it'll be a hot summer. But then the interconnection queue of potential projects, most of which are data center, a little bit of crypto, a little bit of oil and gas, and then just general load growth, is like 400 gigawatts. Like, these numbers don't make any sense. They're just kind of bizarre. Part of that is a legislative requirement in Texas where by law, ERCOT has to add to its queue anybody who says they want to build anything. And then the question is, how much do we discount that? Do we discount it by 80% or not? And that there's like a lot of fight because now people are worried. And by people, I mean like all politicians across the spectrum basically are worried that rates will go up and retirees and grandmothers will have to pay more for electricity to make big companies richer. Like that is the political framing and the concern. And it's gotten so political that Governor Abbott in Texas, like yesterday or the day before, announced that he's not going to allow data centers to get built unless they meet certain requirements around power flexibility, water positivity, carbon negativity, this kind of thing. So Governor Abbott starts to sound like a liberal in terms of his desire to regulate the industry to make sure it's in line with environmental pressures and needs and all that. I'll make one more comment, then I'll be quiet to cede the floor. Part of that queue of 400 gigawatts or whatever it is, these numbers just don't make any sense of new construction is a lot of people who are speculators. There's a lot of real stuff there. And I'm going to share one anecdote from yesterday. I was flying to Boston yesterday, and I think this will diminish all of you in your view of me, so my apologies in advance for that. But I am a high status flyer with American Airlines. Like American Airlines sees me coming, and they're like, "Here comes our moneymaker." I've got as much status on American Airlines as you can have. And because there was weather in Dallas and Charlotte, Chicago, you name it, flights were disrupted everywhere. But as a high status flyer, I have the right on American Airlines to book three itineraries simultaneously and then just go on whichever one gets me there soonest. And I don't have to pay any, like for the same price, I get three itineraries and then I'll finally get one and then the other two clear up. That's what's happening with the data center queue for interconnections, where the high status, the rich data center company, they just enter every queue they can. Texas, Northern Virginia, South Dakota, Alberta, you name it. There's a lot of queue shopping going on. It's kind of like if you go to the grocery store with a family, you might split up with the spouse and the kids into multiple lines to see which line is shortest, and the last minute you consolidate. That's what's happening with data centers as well. So there's a lot of queue shopping going on because they're high status or they have the money or they have the resources. And the last minute, there'll be some consolidation. And we don't know if that consolidation is it 3 to 1, is it 5 to 1, is it 10 to 1? But we know that what is in the queue is not real. Having said that, even if a small fraction of it it's real, is still substantial and significant, and we better prepare for it. And the way I imagine this is like it's pretty exciting to have a rich customer class come into the grid because historically the grid's been expanded for poor people, and now we're expanding the grid for a rich customer class. So we can work with them and say, hey, you got money, you want power. Why don't you invest in the power flexibility and the grid enhancements that improve the grid for everybody? So I actually think that in the end, if we do it the right way with the right kind of flexibility, that this rich customer class will end up improving the grid, expanding the grid, improving the reliability, and lowering rates for everybody. But we don't feel that yet. Anyways, we'll see. Well, I'll stop there, and I look forward to this conversation. I appreciate you inviting me to it.
Thanks, Michael. Yeah, and I'll kick things over to Eric maybe just to add a little bit of the scale to the conversation too, given all the gigawatts that are thrown around here. One thing I always like
Sure.
to try to remind folks is that a gigawatt is like the city of Seattle or San Francisco. Like these are, plop, there goes a city somewhere on the grid. And so that helps understand that when I say analysts of several different analysts out there, obviously lots of different numbers, but recent estimate from Janice Henderson was that only half or only 84 gigawatts of 157 gigawatts of announced AI data center capacity will actually be built by 2030. The Only Framing doing some interesting work there. Only 84 new Seattles plopped onto the onto the US grid. And that's greater than Grid Strategies, who at the end of last year estimated 65 gigawatts of projects likely to be built across the country by 2030. And importantly, that doesn't include another 70 gigawatts of additional peak load growth that utilities are forecasting by 2030 from other sectors besides data centers, right? So we have EVs, we have manufacturing, coming back to the United States in certain cases. We have heating, electrification, and other drivers of demand growth as well. And we basically tapped out the kind of energy efficiency low-hanging fruit that we've been able to mine for the last decade or so, with basically full penetration of LED lights, across that sector, for example. Not a lot of additional gains to be had in lighting, and so that sort of petered out on the efficiency side. So 65 gigawatts, only 65 to 85 gigawatts, right? That's an enormous amount of growth between now and the end of this decade. And of course, the uncertainty as to where exactly on that grid that 84 gigawatts shows up, is it which of those three projects in the queue actually materialize, has outsized impacts on power flows, on constraints, on the economics of other investments going into the system. So that uncertainty, besides the volume, but the actual location, I think is one of the more nuanced and challenging pieces for energy system planning right now, is where actually are these things going to show up, and how do we build infrastructure in advance of the need of a giant city's worth of demand when we don't know if it's going to be over there or over there. So it's a big challenge.
65 gigawatts is the UK, and
Yeah,
85
exactly.
gigawatts
Or
is like
California,
almost
right? Yeah.
France or something like that, right?
Yeah.
In these states, like you're plunking down to Seattle or San Francisco, it's at the end of the block, right? So
Yeah.
it's just like a city, but in the space of a subdivision.
Yeah, of like a Walmart.
Yeah.
Exactly. All right, Eric, over to you. Thanks.
All right, I think I'll share some slides. Well, this has been fascinating. I think I'll reinforce some of these key points that have come up, but I do have a slide deck. Hopefully everyone can see it. I'll try to go through it pretty briefly. But, and I just spoke about this on campus, this very issue of what do we know about the load growth of data centers, particularly driven by AI, where it's headed, what are the unknowns, what can we do as modelers, where do we need to address uncertainties? And I think, just for just level setting, this is a sector that, as we've just discussed, is growing very rapidly. But in terms of our ability to model it, to have real data, to predict where it may be going, to look at different scenarios, our ability is pretty poor compared to those other sectors that Jesse mentioned, manufacturing, buildings, and so forth. So we've all heard about, the insatiable appetite for energy of data centers and the air pollution and the water use and the noise and so forth. These are very real issues. But every one of these stories comes from some number that somebody has published, right? It could be a media outlet, it could be a blogger, it could be ideally someone from the scientific community. So the first thing to understand is there's a lot of numbers floating out there and a lot of uncertainties. And the best numbers are typically coming from the energy systems analyst community, which is the community that we're all part of. But this story goes back 20 years. So the very first study that was commissioned by Congress was back in 2006. And believe it or not, back then they were worried about the load growth of data centers. So they commissioned a study. I was a young researcher at Lawrence Berkeley Lab. I had no idea what a data center was, but I got assigned to the project and have been working on them ever since. But we have to answer questions as modelers, such as how large is the potential load growth? Where is it going? What's driving it? And even more importantly, what do we do about it? Just for context, answering those questions requires more and more data, more complex models, and the uncertainties build up. So the further we go out in time with this fast-moving sectors, the greater the uncertainties. And we've only had 3 national studies in the last 20 years that try to give shape to this problem at the national level. I think that needs to change. And I think this community of macro energy systems modelers is going to play a key role. And the reason for this, why do we need models, you might say? Like, don't we have the data? But the answer is no, we don't have the data. So this is a recent public open publication from Alex DeVries, who's a colleague in the field, where he just did a quick stock take. So if we look at this table, I recognize it's very busy, but in the rows we see the sort of data that energy systems modelers need. We need to know how much electricity, how much water, how much is direct, how much is indirect. In columns we see some of the major players. And if you just scan the table, you'll see that there are a lot of no's. What does that mean? It means that these companies are not reporting key data that analysts need for better models. And this situation really hasn't improved over the last decade or so, and it needs to get a lot better. So this is why we need models. And the particular model that I work with colleagues at Lawrence Berkeley Lab, we've been developing it now for a couple of decades. It's very rich. It's what we call a bottom-up model. It helps us understand the types of servers and different data centers in different locations, their climate variables, how much water will they use, how much energy will they use. These models take a lot of work, they take a lot of data, but they also require a lot of assumptions. And every model is different. So this is a report, results from a report from EPRI, who's also working in the field, where they have a model and they've compared their results to other models and other outlooks. And if you just look at this chart, what do we see, right? It's their projections out to 2030 at the US national level. We see a factor of 5 difference between the lowest estimate and the highest estimate that anyone could grab to form a conclusion about the data center sector. Some of that is irreducible uncertainty, but a lot of it is due to not having the data and not having the best practice standards as modelers that we all need to make sure we're using the best techniques, the best data to provide the best information to energy systems planners and to policymakers. So we certainly have work to do. And what I'd love to do in just a few minutes is just maybe tee up some of the challenges that we face as energy systems modelers when modeling this sector. The first gets right back to what Michael was talking about. How much of the load growth will be real? So some of you may have seen this chart before. There are a bunch of them out there, but what is it showing? X-axis shows years going back to 2010. Y-axis shows gigawatts of IT capacity for data centers. And if you look pre-2022, there were always uncertainties. This was always a difficult sector to model, but it was reasonably stable, right? We were always adding data centers. We always needed, we were always consuming more data. But since the AI boom, this has gone off the charts. And a lot of these very large projects are being proposed. Some of them are being built, some of them are planned, and a lot of them may change, right? So here's an example of a humongous data center where the plans were pulled back, right? So that's something that disappeared from the load growth, terrain, basically. And this can happen all the time. As Michael said, what amount of consolidation is going to occur? We don't know, but it's something that really affects what our outlooks predict for this sector. So that's the first challenge. The second challenge is you might say, well, okay, if you miss the occasional data center here or there, like what's the big deal, right? It used to not be such a big deal when the largest data centers on the planet were, 70 megawatts, maybe 100 megawatts, like this old Facebook data center here on the left-hand side of the graph. Now, these data centers, or I should call them data center campuses, they're most often multiple buildings on the same campus. We're talking about 1 gigawatt, 2 gigawatts. You're hearing about in Utah, 9 gigawatts. That's 90 times the size of some of the largest data centers that were on the planet just a few years ago, right? So we really have to make sure we get some of these numbers right. Otherwise, a load forecast could be very much off. That's challenge number 2. Challenge number 3 is analysts like us, we don't have good data on what's occurring in the actual builds that are being rolled out today. Why is that? A lot of these details are kept secret due to NDAs. So we never really know what's happening on the ground today to calibrate our models. We get numbers often, but they come a year later, 2 years later after these data centers are built. A lot of the technologies and energy and water use are locked in by the time we see the data. That's a third big challenge for us. Fourth challenge is, even if we have some sense of what's going to be built and when it's going to be built for a certain capacity, a data center never runs at 100% power capacity. It's always lower than that, right? There might be peaks, but in general, different types of data centers will have different levels of capacity factor. So this really affects what the real load will be on average. But also, if you look to the right, cooling technologies, the climate, their set points, these really affect what's known as the peak energy load. And this can be a really big load for a large data center. So we also need to start thinking not of just about, well, how many gigawatts will need to be built, but what does that peak load look like, where and when and why, so that we can provide better insights into energy systems planning, because peak loads can put a lot of stress on the grid, but they can also demand a lot of water, and our ability to model them is currently pretty poor. Challenge number 5, this is a landscape that is changing very rapidly, partly due to the enormous pushback we're seeing from communities about data centers, because they're hearing a lot of scary numbers, and when companies don't release real data, whether they're scary or not, communities don't have any real data to go to, and we sort of default to the worst case scenario. And that's the right of communities, right? If companies aren't sharing their data. What this has meant is there's been a lot of projects that have been canceled or pushed back, or technologies changed in light of community opposition, which I'm 100% in support of communities having a say in what gets built for their energy and water resources. But this is rippling into a lot of policies that are being introduced. So my lab also tracks policies that are appearing around the world, but particularly in the US. This graph is already out of date. It was current as of about a month ago. There are dozens and dozens of policies that have been proposed since mid-May, hundreds of them in the US alone, which are planning to regulate data center energy use, renewable requirements, water use. A lot of these policies never get passed. Some of them do. So now an additional challenge for all of us is tracking the policy landscape and making sure we understand what's real and what's not. That's going to shape the trajectory of this industry moving forward. Part 6 of the challenge, there's more, is the fact that a lot of these data centers aren't able to connect to the grid, so they're building their own on-site power generation. We know this is happening. What does that mean for the grid? Is it a good thing? Is it a bad thing? What are the air pollution trade-offs? What are the water trade-offs? This is something we didn't really have to contend with in the past when modeling this sector, but we now do. These are all sort of on the burden side of data centers. But what we absolutely have to acknowledge is the technologies get strikingly more efficient with every generation. So with every data center, server, network device drive, there's constant innovation. These companies are under pressure to reduce their energy use, frankly, from a profit perspective these days. But what are we seeing here? Like a 1,000,000-fold increase in efficiency from the very first NVIDIA GPUs up to what we have today. We have to keep track of this because this will certainly shape the way that energy use will go. And then the last challenge is these companies, as we know, are the richest sector on the planet. When they build a data center, if they can't connect to a green grid or provide renewable electricity, they're investing in something somewhere else, in another grid, maybe nearby or in another country, or they're investing in breakthrough technologies. So what does this all mean for the energy system? We can't just keep track of what's being built and where and what they're drawing. That's important, of course, but sometimes they're making investments in other grids to offset their emissions or impacts that we need to keep track of as well. So now there are a lot of moving parts from an energy systems modeling perspective. And I'll just wrap up by saying, what are some of the key trends that we really need to follow? And I'll just go through them right here, right? So we've got to be better aware of where data centers are being sited. They're not often always sited in the best places for renewables and water. They're finding available land, they're finding available power, they're finding where they can connect to power or build their own power. That's what's driving siting, but it really matters for local grids. There are stringent efficiency standards that we're seeing appear here and there around the country, around the world, mandating things like PUE limits or WE limits. Waste heat recovery, number 3, this could be a big one. So waste heat is always there in a data center. Every single data center converts electricity into information and has waste heat, right? We all know that from working on your laptop on your lap. You never ever done that, your legs get warm, right? That heat has to be removed. And in the past, with air-cooled racks, it wasn't really economical, or there wasn't the level of, heat throughput or quality of heat for waste heat recovery. That's potentially changing with very large data centers. If you've got a 1 gigawatt data center, you're generating a lot of heat that could potentially be reused for building heating in parts of the world like Europe and Asia where they have district heating. You could use it for on-site cooling. You could use it to run a DAC unit. You could use it for an industrial facility nearby. So the systems aspects of modeling this sector are also, growing in terms of their complexity. But maybe electricity use by a large data center, if we can recover some of that heat and reuse it elsewhere, it'll have beneficial effects elsewhere. Who knows, but we need to get better at modeling it. We've got to pay attention to peaks. We definitely need more data from the operator so we have better models. We can't validate our models because we don't have the real data to validate them against. That's a problem for all of us. And the last 2 bits are, we're seeing the early days of AI with large language models and really complex models getting a lot of the attention. But we can't forget that, AI is a humongous umbrella for many different types of models, machine learning models and others. Smaller models that are designed to do medical diagnoses or to solve cancer aren't going to require the same amount of energy and compute that you need for a large language model trained on trillions of data points, right? So as we're learning about AI as a society, there'll be opportunities for much smaller models that can run on much less compute moving forward that we need to keep track of. And then the last sort of big, question for us is the net balance there. Michael alluded to this. Like if AI can solve problems in one sector through its applications, we already know that AI can make building energy controls more efficient than standard controls. It might be able to optimize logistics. It might be able to better diagnose disease. It might be able to solve cancer, right? These are all the big hopes that the tech industry loves to point to. And I think some of those will come to pass. But as analysts, we don't have the frameworks, the data to really understand this net balance between the burdens we're seeing today. It's all front loaded. We're paying the price for AI right now in the hopes that in the future, we can save more impacts than we create. But in order to understand if we're heading in the right direction, modelers like all of us need to start thinking about the frameworks, the net accounting that we need to do, the data we need, because right now we're sort of operating in the dark and we have no way to verify claims of AI providing more benefit than it does cost to society. So these are the grand challenges for modelers that I'd like to leave you with. And with that, I'll turn it back over to you, Jesse.
That was a great intro, Eric. And yeah, it's I think Michael said always exciting times in energy. I don't know that that's ever not been true in the 20 years I've been doing this, but this seems like a particularly exciting moment given the central role that electricity plays in powering this sort of next generation of innovation and economic opportunity, but also, of course, the huge potential local impacts that are unfolding across the country. Michael, I think you alluded to the fact that if we do this right, we have a deep-pocketed set of electricity users who, for whom the electricity consumption is a pretty small fraction of the total cost of a data center, right? Which is partly why they have that potential willingness to pay. So if we do this right, we have a potential, payer to build out the next generation of our grid infrastructure. Of course, if we do this wrong, maybe not. So what do you think is when you say do this right, what do you have in mind? What are the things that we have to get right? And are we doing anything close to that?
Yeah, fundamentally, it is exciting because the grid expansion will be for a different purpose now than when we've done it in the past. In the past, it's always been about residential consumers or appliances like air conditioning, and we will benefit if the grid is improved for other users, but there's some broad-based reliability enhancement or better utilization of the assets, which lowers the cost. So there's a way I can imagine where it would go better. But I think it means a couple things. I think it really means that data center developers or operators or the tenants or the hyperscaler developers, whoever the right stakeholders are, can do things flexibly. And I think flexibility could be computational flexibility, like or algorithmic flexibility, where you just kind of change maybe the clocking speed of your chips to reduce demand. You could have on-site storage or on-site power generation, where you just pull power from a different place at peak times. Because really, we have so much excess capacity in the grid and so many extra terawatt hours we can provide most of the time. It's really just that 1 to 10% of the time when things are scarce. So how are data centers operators going to work then? And what technology we have? So I think for me, a lot of the doing it right is flexibility. Now, it doesn't mean that the data center has to be flexible. They might convince other people near them to be flexible, or there's a lot of ways you can do this. So, and I know you're so deep on this, Jesse, right? But I think that's the first thing. The next thing is we don't want data centers to be additive when it comes to emissions. There's a lot of technology substitutions that happen. An electric heat pump in place of a gas furnace. Yeah, that drives up electric demand, but it reduces gas demand somewhere else. Electric vehicles here displace gasoline there. AI data centers are additive. It's not clear what they're displacing. They might displace something yet. So the fact that they are additive really implies like the sourcing they use for the power will matter because it's additive. And most of them recognize this. None of them want coal. They want nuclear, geothermal, wind, solar, batteries, and natural gas if they gotta. And that's kind of where we are. And I think they're open to using the waste heat, as Eric said, for carbon capture or direct air capture, something like that. So, in my opinion, power flexible and carbon negative is the way to go. And then the third is water positive. Water positive meaning they need water for the water cooling because the chip density, the power density is so high, it's hard to get there with air cooling. So you need at least a water loop inside the building, maybe a water loop outside the building, but that could be air cooling or something else. But if you take the money you have and invest in water systems nearby. Meta's doing this in El Paso, for example. They're saying their data center will be water positive. They'll invest in wetlands or other water infrastructure so that the community actually has more water when they're done in the end. And there's a lot of inefficient use of water for irrigating alfalfa or something like that. And so so they do it right just really means power flexible, carbon negative, water positive. And I would also say tax base positive. Loudoun County in Virginia has lower taxes now because data centers have paid so much taxes. That's great. But there are a lot of states doing like the multi-billion-dollar tax breaks and things like that.
Tax abatements.
Where it's like, yes, it's like, oh, wait, the community is gonna have all the trucks and the noise and the heat pollution and light pollution, blah, blah, blah. And they don't even get like new courthouses and playing fields and schools and libraries out of it. So it's got to be
what's in it for them, right?
Yeah. So people get pissed. So I think that's kind of the way to do it right. Like, okay, what does the community need? How do they feel bought in as a part of all this? And that's what I think about. And I would say one more comment on power flexibility. 2 years ago, when I was talking to hyperscalers, I say, hey, can you be power flexible? Absolutely not. We're in an arms race. It takes 9 months to train a large language model. We can't dial back for 15 minutes. Now you're like, hey, can you be flexible? And if you are flexible, you can hook up to power sooner. They're like, oh, yeah, we're open.
Yeah.
So the mood has changed a lot in 2 years around flexibility, I would say.
Yeah. Yeah, my concern, I mean, there is a lot of excess capacity on the grid if you can sort of work around those, less than 1% of hours when the network is binding or you're dispatching all of your available peak capacity or calling on demand response. The challenge is what's available on the grid is, the resources that are not cost effective enough to dispatch under normal load. And that means basically less efficient coal and gas generators that'll then get called in to step in to meet that additional demand outside of those 1% of peak hours. And so I think what you said, Michael, about the need to bring in new clean energy to power that kind of 8760 operation is the other big piece of the puzzle. And I worry that there's a lot of motivation and a lot of money to be made to sort of unlock that flexibility and get on the grid faster. But then there's not a ton of incentive to tap into that clean energy other than for environmental goals. And so what our company at Firm is trying to do is trying to make that the fastest, easiest path to power. There's a lot of complexity involved in putting together a portfolio of wind, solar, and storage resources that can actually be built now, not nuclear, that can be built in the 2030s, right? And get that to market quickly in the right combination that's deliverable to where people are. So we're going to take on that complexity and try to make it easy. But absent that, it's kind of clear why a lot of data centers are pushing to gas, right? You're seeing huge build outs of on-site gas because it both solves the grid interconnection problem and then they can run at 8760 and power their operations. And these are not generally large, efficient combined cycle power plants. They're often a whole fleet of much smaller air derivative, combustion turbines or even reciprocating engines.
Yeah, I would say a lot of reciprocating engines are getting built for this.
Yeah, so, which is, these are generators designed ideally for backup operation, not for 8760 operation. So it's quite quite challenging from an air pollution perspective for the local community as well, and from a noise pollution perspective. I heard somebody describe it as having a fleet of 100 semi trucks idling nonstop right in your backyard, and so you can understand why folks might not be so excited about that.
You move to the country to avoid the noise of the city.
Yeah, but now you've got a fleet of reciprocating engines running nonstop. So Eric, what do you think about the challenge of sort of doing this the right way and harnessing this opportunity to kind of build out the infrastructure we want and maybe avoid a large push to inefficient gas generation?
Yeah, I think this is a great conversation, and we should also acknowledge a lot of those burdens are being borne by disadvantaged communities, that sort of thing, right? So, like the burden sharing in this proposition so far isn't at all equal, right? A lot of people stand to gain, and a lot of people stand to bear the burdens in sort of unjust ways. So it's a really tough time to, I think, make sense of this sector because it's in a like Michael used the term arms race. We're still seeing that, right? Huge amounts of investment, some of it speculative. If there are guardrails in one location, for example, mandating behind the meter storage or some fraction of renewable energy or a PUE maximum, that sort of thing. There is another jurisdiction somewhere that has the exact opposite, right? Loads of incentives. But I think in general, if I could just go ratchet up to the 50,000 foot level and say, what would a more sustainable AI data center sector look like, right? Well, we absolutely need maximum efficiency standards. What does that mean? So, for example, there's some interesting trends happening. So with AI racks, they're running at a lot greater power density. They generate a lot more heat. That demands a shift to liquid cooling. If anyone heard about the NVIDIA announcement a few months ago at the Consumer Electronics Show, Jensen Huang mentioned that we can now run our AI racks chillerless, basically, and cool them with hot water. What did he mean by that? 45°C, like cooling water coming in, that's pretty hot, right? That's about the temperature you have in your hot water tank at home. And then you get maybe 55°C water coming out, which you can pretty easily reject into the outdoor environment as long as the dry bulb temperature is 40 or less, right? Which it is in most parts of the country. At most times a day, then perhaps dry cooling could be rolled out to reduce water stress where we want to reduce water, right? So more sustainability means like really focusing on what's needed locally. So in water stressed areas, potentially shifting to dry cooling at high rack temperatures, which doesn't come with the same energy penalty as you would with traditional dry coolers running at 25°C or something for rack temperatures. Renewable energy requirements, whether that is today or in the near future, right? So one problem I see with all of the big bets that are being placed by tech, which is great. They're investing in small modular reactors and fusion and geothermal. We don't yet know when those will come to pass. There are no sort of firm deadlines and targets for them to make up for the emissions that they're emitting in the short run, right? Through on-site generation. So some sort of renewable energy requirements and some hard deadlines around that. I think some demand flexibility is certainly in order. If you look at the value proposition, though, it's still pretty tough. If you just take the investment in the compute, billions of millions of dollars, right? And the amount of compute value you get per kilowatt hour, that's much higher than the cost of electricity, even if you can subsidize it with demand response. You know that well, Jesse, right?
Yeah, it's got to be a capacity opportunity, right? The fact that because you're able to be flexible in a few hours, you can then deploy more capacity and more chips onto the grid faster, right?
Yeah, sure. So how do we acknowledge that, right? Through either regulation or creative financing, that sort of thing. So there are a lot of technical solutions. I do think we need more transparency so that policymakers can make sensible decisions. Right now, it's either come one, come all, or we're going to ban you. And of course, neither one is good from a practical sustainability perspective. So what does that look like? But maximum efficiency, energy and water use that are appropriate for the grid. We want low emission standards, ideally not just for carbon, but also for air pollutants, because we're seeing an uptick there as well. And sort of what that solution looks like is going to vary based on location and jurisdiction and the energy grid and the available water. So there's no one size fits all. But I do think we have all of the tools we need to make the sector more sustainable and to get to that endpoint in the future. And then I think transparency. We need the data to monitor and measure and know if the policy outcomes we're trying to achieve are actually being met. We don't have that today. And then we need better frameworks for understanding the net benefits. If we're going to save more energy somewhere through building an AI data center that uses energy here, we need to understand what those trade-offs are going to be for sensible decisions. And right now we're all sort of operating in the dark.
So on that data and transparency side, Robbie Orvis asks, is there any data or sources you can suggest for evaluating seasonal load factors or the kind of performance consumption curves over time for data centers? I think we often have thought of them as base load run 24/7, but I think as you're pointing out, that's not actually the case, and they may only rarely use their peak capacity on peak cooling days. So What have you seen as the best available sources for that?
So we don't have a lot of great data on load shapes. It's getting better. So for example, my colleagues at LBNL are starting to simulate load shapes for different types of workloads, for different types of data centers. This would just be the compute load. You'd have to layer on top of that the cooling load. So it's getting better. EPRI has a few, that sort of thing. But it wasn't an issue, frankly, for data centers in the past because they were small and we assumed that they were flat and they almost didn't matter from a good perspective for the most part. Now that's changed. So the IT loads, we're seeing some load shapes come out and keep watching for those, but no companies are releasing them. It's more or less simulations. On the cooling side, we have pretty good models. So for example, my lab has a physics-based models that we've maintained. Others do as well, where you can predict with reasonable accuracy. It's never perfect what that cooling peak is going to look like, depending on the climate, your set points, your core cooling technology, whether it's evaporative or not. So there are better pieces now for people to sort of understand load shapes, IT and cooling at a hyper local level. And feel free to reach out to me after the call. I'll send you the papers I'm aware of, the resources I'm aware of. But it's getting better.
Is that an open source model, Eric, or is that something you
It's open source, We're updating it now. We'll have an online calculator later this summer as well.
Okay. Yeah, and Robbie, keep an eye out for work from Zero Lab. We're trying to incorporate resistor capacitor based models to represent the heating systems. They'll be incorporated and can be tractable in a capacity expansion planning context as well, so we can kind of represent that directly in the capacity expansion models.
And a quick comment on that, I think we all want the data and the load shapes. We'd all love that for our planning. The operators or trainers of the models might not want to change their computational behavior during the day at peak times, but thermal behavior is so predictable. You can do simple stuff like making ice water and all that kind of stuff. Like thermal storage would be great for peak shaving because your chips will be hot at peak time. So there's part of the load that's super predictable, as Eric said, and pretty easy with off-the-shelf technology to at least shave the peak a little bit. And I think that can be done. And I haven't heard of that many thermal storage projects at data centers, even though that's a pretty straightforward thing.
Yeah, we're just about to complete a project in 2 weeks, a final workshop that National Lab of the Rockies has led on using underground thermal energy storage for cooling at data centers, or more efficiently cooling them, but also primarily peak load. You drop the peak load to like a fifth of what you would otherwise have for cooling, and that frees up a huge amount. We're also exploring cold water storage, which we have on the campus here at Princeton, and we do that with our systems already. It's just a big tank of cold water, so nothing fancy there.
UT's at peak demand is like 100 megawatts or more. Yeah, we have 10 million gallons of chill water. So 100 megawatts, that's University of Texas campus. That's kind of a data center, right? So you can do thermal storage at the level of the data center. And so of the two picks, computational peak and cooling peak, at least one of them you can see coming and manage that a little bit.
Michael, you mentioned the water use. I mean, I think a lot of systems are moving more towards air-cooled operations as well, because they can't, get the water for evaporative cooling, and that drives a much larger delta, right, between on-peak consumption and off-peak for the cooling system. So that's another. It might be like 10% on average of the demand might go to the cooling system, but at peak it could be more like 30 or 40%.
I mean, this is a big issue because water is more sensitive. Like in Texas, we argue about whether climate science is real,
Texas, right?
But we don't argue about whether water is scarce, and water is important, at least in the western half of the state. Microsoft is building a data center outside of San Antonio in Medina, and they wanted 1 million gallons a day of water for their water cooling. And the local utilities like, we'd love for you to come to town. They wanted the data center, but you got to go to air cooling. We can't give you the. So air cooling, now all of a sudden they only need 15% of that water. So it's 150,000 gallons a day instead of 1 million gallons a day, but their energy demand will be higher.
That's it's a water energy trade-off.
Yeah, it's like, okay, so it's less water, but then now you have an efficiency penalty. And I think it's probably easier, at least in Texas, to come up with more electrons than gallons of water. So that's okay, but that's not an easy trade-off everywhere necessarily.
All right, so I got a question from Emil Demanchev, who's in my group here at Princeton. What's the best way to ensure that no undue cost is shifted onto other consumers? And this has become like basically table stakes now. If you want to build a data center, you got to show that you're not driving up electricity prices, because that's been a central concern around the country. So have either of you seen models emerge that you think are effective in that space?
I don't know if I've seen a model, but I will say that this first emerged in Texas around 2022 around crypto mining. And crypto mining, I think, has kind of tarnished the whole AI industry, frankly, because people don't know the difference. And crypto mining is kind of like, well, use a lot of power and we're not even sure what good it does. AI, you can imagine some good it might do. And so crypto is an issue. And I remember Senator Elizabeth Warren from Massachusetts saying basically the same things as Lieutenant Governor Dan Patrick in Texas. So you had ultra left and ultra right both saying, we don't want grandmother subsidizing Microsoft. It was kind of the theme of what they're going on.
Yeah.
So how do you protect the rate classes? And that's hard to do. I would say it as a former regulator for Austin Energy, where I've been through rate making processes. Rate design is hard because there's always some cross subsidy potentially, unless you do a full cost of service for every rate class. Rate classes tend to be residential, commercial, industrial. Then you have like some city stuff like traffic lights or something. But if you really want to do a full cost of service study, residential is really expensive to serve because the consumption per meter is quite low and the variability is quite high. Industrial tends to be much easier to serve because its round the clock use is much higher and it's more use per meter, which is why industrial rates are lower than residential, but not quite to the cost. So there's all usually cross subsidy. Industry is kind of subsidizing residential a little bit in most places in America. And I think people are comfortable with that flow, including even industry, frankly. But making sure it doesn't go the other way is the most critical thing I'd say. And sometimes it can be a direct transaction. I think isn't it Google's been talking about paying neighbors in the area, 10,000 people to do demand response, right? So it can be directly from the consumer, Google to them, or you can build that into rate making. So there's a lot of good ideas out there, but I don't know if I've seen a successful example of it yet.
It's a bit out of my wheelhouse because I focus mostly on the demand side, but we have heard of pledges, right, at the national level for data centers to pay their own way.
Yeah.
But I don't have a good sense of how that would work. Michael, you probably have a much better sense of just the heterogeneity in the way rates are set by grid, by state, like how that would actually look if we can hold them to it. I don't know. Those are open questions for me.
Yeah, it tends to be a pretty case by case, issue, right? Because each utility is in a different,
So
construct, responsible
localized,
for different pieces
highly,
of
highly
it, and has different
localized.
control. I think one of the biggest challenges I've seen is in PJM, where we live here in New Jersey, which is a very markets-based approach, where we have a capacity market that is centralized. Everyone has to participate in it, as opposed to the kind of mixed bilateral centralized construct in MISO, or the fully bilateral construct in SPP in California. And what that means is that, in order to induce more capacity to enter the system, we typically rely on higher prices to induce that new capacity, right? And so you throw a few, tens of gigawatts of demand growth into that story, and the demand curve is quite steep, and the price goes up very rapidly. And so prices have soared for capacity in the PJM market, kind of flipping from oversupply to undersupply, and right up to a level that was deemed pretty quickly not politically sustainable. So governors in the region, including Governor Shapiro in Pennsylvania, basically sued and settled by imposing to get PJM to impose a price cap on that market. And so now you have a price signal that's high, but not high enough to actually induce new entry. And so we're not getting any new entry, and they're going to secondary markets, and it just sort of becomes a mess. And so what I've seen to be most effective seems to be bilateral contracts, where you basically say, look, if you want to connect to our grid, you bring the capacity you need to offset your load. And you pay for that bilaterally, and we settle that outside of these centralized markets, so that the supply curve moves out along with the demand curve, right? And then the prices are going to settle basically in the same place for the broader market. And we've seen that come in a few markets for capacity. I've seen it less commonly for energy, which in all of these markets relies on energy transactions that will have a similar dynamic, where you throw another Seattle worth of baseload demand, and prices have to rise to induce the less efficient generators to get off the sidelines and dispatch, and then everybody's paying a higher clearing price in those markets. So it becomes tricky, and in some ways, you kind of have to short circuit the logic of the centralized market with bilateral side payments if you want to avoid that kind of effect in a market context. In regulated markets where everything's kind of vertically integrated and funded via cost of service, then you do something more like you said, Michael, where you just run the rate case and you figure out, what do I need to take out of this big chunk of money and allocate to the new load to make sure that the rates don't go up for everybody else, and maybe you have more flexibility in that kind of context. Let's see. What about this uncertainty question? So Silas, also in my group, asked, any favorite innovative contract arrangements for data centers to make commitments to grid construction, for example, that would reduce this uncertainty about, are you going to locate here or there or the other place, right? Lead times for building transmission and substations are long, and you don't want to spend, $1 billion building a high voltage, DC, AC upgrade to a, 345 kV line or something, and then have the loads show up somewhere else. So are there any ideas out there for how we can, get the data centers to signal greater commitment, or find some other way to resolve this uncertainty?
I'm going to steal a line from Josh Rhodes. So Dr. Josh Rhodes at UT, he and I work together on a lot of things, and he's really smart on these issues. And he often talks about what AESO, the Alberta Energy System Operator, does in Canada. What they do for power plants could be applied to load. So for power plants, a new power plant comes to town, so to speak, comes region. they have to pay for the grid connections for their power plant to be sold to the market, but then they are reimbursed over some time, like say over a decade. And so that means that they pay for all the upgrades and they're slowly reimbursed, and it prevents the risk that they're going to build a power plant, saddle the region with expensive upgrades, and then disappear in 2 years. So it protects the local ratepayers from fly-by-night power plant developers who might not be in it for the long haul. But if they are in it for the long haul, they get paid back for the upgrades they did. And we can take the same concept and flip it to load. A large factory or a large data center needs a bunch of upgrades that costs hundreds of millions of dollars. They could pay for it. And then if it really does benefit more than just them as consumer, like has some broader grid benefit, they get reimbursed over some time. And if it's a fly-by-night speculator building a data center that doesn't have a tenant, then they don't get their money back, but no one's saddled with it. So there are some approaches that have been used on the generation side we could apply to the load side that at least protects the local consumers, also becomes a test, a discriminating test about whether the developer is serious. Are they speculating?
Yeah, they got to post some serious collateral to do that, right?
Put some money on the table, right? Your table stakes should be, we're going to upgrade the grid. And frankly, when I talk to the big developers, they're on board with that. And to be clear, not everyone knows this. The hyperscalers we think of, the Microsoft, the Meta, the Amazon, and Google, are not the developers. They're often the tenant. It's someone else who's the developer. Someone else is building the data center that then, say, Microsoft is the tenant and rents in. And so some of those developers, they have land but don't have a tenant. They're very speculative. And then using the money to test for seriousness has all sorts of cost of market entry problems, which you wouldn't like from a capitalism theory, but does have great benefits of protecting the ratepayers from non-serious developers, I would say. And so I'm a fan of that. And I think when you're in this kind of land rush situation, you need to have something like that to help you determine who's for real and who's not.
Eric, anything you want to add?
Just add, I don't have a lot to add to that. It's really great perspective. If there are arrangements for demand flexibility or load shifting, whatever, we need to have the data, the accounting frameworks to monitor and verify that, like we do for other sectors, and we don't yet really have that so much for these large data centers.
Yeah, they need to be fully
right?
dispatchable and have the same kind of telemetry that a utility can count on that they might expect from a storage operation or something like that as well. A question from Dominique, who asks, I'm a master's grad here. Where should someone look to transition their career into this area? How can we contribute to making this space carbon negative or build new infrastructure through AI and the data center build out? A couple of professors here. Any thoughts on
there are so many jobs. So the economy is weird. And a lot of coders have been laid off. Hundreds of thousands of coders have been laid off in the last couple of years. But I see so many positions open. You think on the power plant side, look at Fervo Energy doing geothermal or all the nuclear startup. They all want engineers, planners, developers, modelers. So the power plants want it. The utilities doing the transmission distribution, they're desperate for people. They're losing their people to all the hyperscalers. So they're looking to hire engineers and planners and others. So a lot of engineering job, almost like not quite technician work, but there's a lot of that as well. Hundreds of thousands of electricians are also needed. Then you get to the large loads, the data centers, the factories, they all need people. So there's actually a lot of hiring going on right now. And hundreds of thousands to millions of those jobs nationwide in the United States are technical jobs, technician jobs, pipe fitters, welders, electricians, that kind of thing.
Yeah, it's a great time to be in the trades.
Oh, absolutely. But there's still thousands of jobs that are sort of the analytical, either financial or engineering analysis to do the studies to help the technicians figure out. Yeah, so there's thousands of jobs. And I would say if you are quantitative at all, either quantitative for finance or quantitative for engineering, there are jobs out there for sure right now, all up and down that supply chain in there. So because even the big consumers, the Walmarts and data centers world, they have large. I think Walmart has like 120 energy specialists on there. So you don't have to go to an energy company even to be in the energy industry on this. And then data centers are hiring their energy experts now. So there's a lot of hiring right now, is what it looks like to me. And now with the resurgence in domestic manufacturing, you can go to a solar panel manufacturer or a battery manufacturer. Or it just looks like it's a pretty exciting time to be in energy. And utilities, which is a place you'd go if you want to do the same thing your grandfather did, are now a place of innovation where they're doing a lot of the things that we wouldn't have expected them to do 20 years ago. So I think there's a lot of job opportunities out there for sure.
Yeah, a lot of money flowing into the sector. There's no doubt about that, and a lot of big challenges that need to be addressed. I'll just double down on the analytical recommendation that Michael made, being a numbers geek. So if you enjoy engineering analysis, there's a strong need for people who can simulate this sector, to predict loads, understand dynamics, do a life cycle balance calculation. these jobs exist across the spectrum of sectors, right? So policymakers are starting to try to regulate a lot of data center aspects, but they don't have the technical, let's say, analysis know-how to really know how to set targets or this or that, right? That's a gap. Public sector, EPA, DOE, others who are looking at, investing in technologies or supporting programs need people who can understand how data centers operate, how to quantify it, how to quantify interactions with the grid, how to do simulations. The companies surely need this. Frankly, the companies are in a bit of a PR nightmare now with all the public pushback. And there's some trust that needs to be built up with getting out numbers from companies, I think, in order to say, hey, our emissions here are X, but over here they're Y, and we're net zero, that kind of thing. And then, tons of startups, right? I was just interviewing with a French news outlet this morning about this new investment from Peter Thiel. It's I'm going to mispronounce it. Parnassus or something. It's a wave energy company. And wave energy, as I know Michael, like it's been around forever, but investments have always been pretty low. So they developed some sort of floating, bobbing thing that basically will spit up water inside and run it through turbines and deploy servers out in the open ocean. So like there's tons of innovation and startups happening around trying to solve the data center energy, power, water, location crunch that I think if you're a hands-on engineer, there are some of those opportunities as well.
Yeah, that's you've got a ton of capital trying to run into some brick walls of real physical infrastructure barriers, and that's always a recipe for innovation. Yeah, you mentioned Panthalassa, which is the wave energy company. They're sort of with these remote little floating data centers out in the ocean. I think in China they actually deployed an underwater data center in the ocean that sort of uses the ocean water for cooling. And of course, SpaceX, of course, just went public with an enormous IPO, and part of their story, at least, which I don't know if I believe it, but a part of their story is data centers in space. Every time I hear that, I think, man, it must be hard to build here on Earth if we're talking about sending data centers to space. So, Michael, you mentioned how, in Texas, the big advantage has been time to power. It's a lot easier to get your data centers online and for that matter, your energy supply online in Texas than just about anywhere else. So if we're trying to avoid having to put our data centers in space and we actually want to build these things on Earth in a reasonable time frame, what can we learn from Texas? I'll let you, get your Texas patriotism.
Yeah, I love it.
But let's get concrete. What should we be looking at there to replicate across the country?
There's a key approach that Texas uses, at least for the generation side, called connect and manage, where instead of doing many years of studies to guarantee that the full output of your power plant will always be able to get to market in Texas, they instead say, we'll connect you and we'll manage it. And there might be times you have to curtail. So we built a lot of power plants in Texas quickly because sometimes they're curtailed. The transmission lines are congested. They can't quite get the electrons to the market, so to speak. But that congestion then becomes an important way to do price discovery of where the congestion is. And then we go, oh, now we know where to build the transmission. So instead of saying, oh, we might need power plants, then decide what transmission to build, we say, go ahead and build it. But you're risking your own dime that you might not be able to sell all your power all the time. So we have a lot of wind and solar power plants that are curtailed part of the year, for example, because of the connected managed approach. It's much faster, but then it also lets us move faster on transmission because it's more obvious where we need the transmission, so we get a double benefit of it. And I think that's a very specific policy example that ERCOT does that the other grids do not do that I think would be good to adopt. And we can adopt it for load, perhaps, which is, okay, you want to build a big, whatever it is, data center or factory, go ahead. We can't guarantee you're going to get all the power you need all the time, though. You're at your own risk. I mean, we're working on it kind of thing. We're in good faith can try to get you what you need. But if you're really worried about it, you might need to build some on-site generation or something. So a 400 or 600 megawatt data center might only get like a firm guarantee for 200 of it and need some flexibility on the rest. And so there's kind of just like a flexibility. It's weird because I don't think of Texas as a high trust environment, but actually it is kind of a high trust environment. They're like, hey, just connect quickly, we'll figure it out. And we kind of go with that. And there's enough evidence now that that's worked. So I think the connect and manage approach for generation being applied to load looks pretty promising. And again, Josh Rhodes wrote a piece on that, so I'm really just citing him. But that's an example. It also helps that, I mean, we're different than New Jersey. We don't have the population density of New Jersey. The number of people we have per square mile is just so much smaller. We have this space, and that's a fundamental constraint that I think we can't throw aside. That it matters. Where in California you have a lot of coastline and mountains, you don't have as many places to build. New Jersey's small, you don't have a lot of places to build. Texas, we got lots of space. In Northern Virginia, you're running out of space. So the density actually will matter for a lot of this as well.
Yeah, governors don't always like to hear it, but it isn't necessarily true that every trend has to go to every state. It's not necessarily New Jersey's destiny to have a giant data center cluster here. It's probably not something we want to be courting. Yeah, the flexible, like the connect and manage approach on load, we Zero Lab put out a report with Camus and Encore at the end of last year on what we call kind of flexible interconnection, which is the same idea on the load side. And the key right now is like you can, right now you either, the obligation of utilities to serve load has always been like you serve load, right? That's your requirement. That's part of your franchise monopoly, right? An obligation to serve. That's what the utilities sort of get this right to be a network monopoly in exchange for. Now you have loads that are basically saying, look, we are okay with, coming online and being, flexible with some portion of it. But right now we have a challenge where it's either 400 megawatts of firm connection or none, right? And then you're entirely behind the meter or you're entirely on the grid. And what the flexible interconnection option does, or the connect and manage option, it says, look, build me the 400 megawatt substation, even if you can only guarantee 200 megawatts of that is firm. Now I know I only need 200 megawatts of additional capacity, and I don't need to run it all the time. I just need to run it when you tell me to turn down my load. And that's a very different picture from these gas plants that are running 24/7 because they couldn't get the grid connection in the first place. So if we do want on-site generation, ideally storage, but even if it's gas, to play a very low capacity factor role, we need to be able to do this sort of flexible interconnection role where we allow for projects to connect kind of up to their full nameplate capacity, even if not all of that is firm. One of the challenges, I think, is that utilities aren't used to doing that. And so it's hard for them to tell the load, okay, this is an expectation of how many hours I might have to curtail you, because they're not running 8, 7, 60 hourly modeling right now. They're modeling a few peak conditions that they know are grid stress conditions under a bunch of contingencies. And so they can tell you under those specific moments whether or not, we think we can serve your load, but they can't tell you if it's 1 hour or 100 hours or 1,000 hours of congestion, and that becomes a big risk for the data centers to take on without any further knowledge. So this is an area where modeling and improvement could actually, coming into practice at the utility side, could actually help facilitate this. If we know we've run the power flows for 8, 7, 60 hours, we know that it's only these 60 hours of the year and these seasons that are likely to be binding, and the event only tends to last 8 hours or less, then you can say, oh, great, I can build a battery. Maybe it's a 10-hour battery, but I can get the job done with a battery. If they tell you it's going to be 30 hours at a time, then either you need long duration storage or you need a gas plant. And until data center operators have a better feel for what that is, it's hard to design anything that isn't a kind of fully dispatchable generator as a solution for that kind of problem. I think we have one more question from Dominica. Is there any particular source you can recommend for those looking to learn more about Connect and Manage? I've got the link to the report there, but any other recommendations, Michael, for or folks?
No, I think Josh is the expert, so I always defer to his writing on that. So I think that's good.
Sounds good. Well, I think we're just about out of time here, and I don't see any more questions in the chat. So Michael and Eric, thanks for spending the time with the Macro Energy Systems community today, and for talking about the topic that is on almost everybody's minds these days. So thank you for joining us, and it's been great.
Thank you so much.
Thanks, Jesse. It's been a blast.
Of course. Thank you, all of you. Thank you, Jesse, Michael, and Eric, for this exciting discussion. And we encourage the community to continue engaging with the MES activities and events. And thank you all for joining today. Bye, everyone.
Take care, everybody.